Today we will go over section 2.1, which is a derivative function. So what is a derivative? To put it in simple terms, it is what we have been doing with limits, but now made easier. Previously we encountered limits in this form right here, and that's what we've been using up to this point. And we interpreted limits in two ways. One, it gives us the slope of the tangent, and two, it gives us the instantaneous rate of change. And since these concepts play a huge role in calculus and will be using a lot in the future as well, limits are put into a new concept called derivatives. And it is specifically called the derivative of fx at x equals a, which a is any number. And the term f prime of a is used to describe this notation right here. So this notation shows the derivative of function fx in this case, and you can see that the derivative equals the limit right here. So they're basically the same thing, but adapted to an easier concept. So an example question to show you guys how limits and derivatives are the same. We're going to determine the derivative of fx equaling to x squared at x equals -3. And I will be using the formula that they gave us in the box. So I'm going to go ahead and plug in -3 into my x's. So I'm going to say f prime, which is x, when I have -3 over here, will equal to limit as h approaches 0, f, and I plugged in my x again, -3, plus h, and then minus f -3 all over h. And from here, what I'm going to do is plug in what I have here to my original equation, which is x squared. So when I do that, I'm going to get limit as h approaches to 0, plug that back in, so I'm going to get -3 plus h squared minus -3 squared all over h. From here, I can solve it further, so limit as h approaches to 0, I have 9 minus 6h plus h squared, and then minus 9 from here, all over h. And then here I can see that this 9 and this 9 cancels out because positive and negative, and I see that I can actually take out h from them, so I'm going to take out h. I have now -6 plus h all over h, and don't forget your limits whenever you're writing it because we didn't plug in 0 in the place of h yet. So now I can go ahead and cancel h's out, and I see that I'm left with -6 plus h. I'm going to go ahead and plug in 0 for my h, and my answer is going to be -6. So therefore I can say the derivative of fx equals x squared at x equals -3 is -6. So another type of problem that they may ask you is determining the derivative of fx equals x squared, which is the same thing we did previously, at an arbitrary value of x. So don't let this confuse you. The only thing it's asking for is you to find it in terms of x. So let me show you. We're going to use the exact same formula, which is the derivative of x, but this time they didn't give you x equals a value, which was x equals -3 in the previous example. So now I'm going to leave alone the x and write my formula as it is. So limit as h approaches to 0, I had fx plus h minus fx all over h. But now I'm going to plug this values back into my y value over here. So I will be getting limit as h approaches to 0. Plug that back in. I'm going to have x plus h squared minus x squared all over h. If I expand this further, I'm going to get x squared plus 2hx plus h squared and minus x squared all over h. I see that I have a positive x over here, so cancel this one and the negative one out. And I see that I have two h's over here, which I can take out. So I'm going to say limit as h approaches 0 again. Take h out. You're going to have 2x plus h left inside all over h. I can cancel these ones out, plug 0 back into the h value, and you will end up with 2x. So that will be your arbitrary value. The second part of this question is asking, determine the slopes of the tangents to the parabola y equals x squared, which is the same function as a, at x equals -2, 0, and 1. So what this means, remember previously when I was explaining how derivative is the same thing as the limits and we interpreted limits in two ways. One of the ways we used limits was to find the slope of these tangents. So the derivative is exactly the same thing. I actually found the function for my slope, which is 2x right over here. All I need to do is plug in these x values that are given, and you would actually determine the slope at this exact point. So what I'm going to do is say, let's say for x equals -2, let's start with that. So the derivative at -2 would equal to 2 times -2, which would give you -4. So this is one of the slopes. Another slope is at 0, which I can find by plugging in at 0. It's just going to be 0. Another one is x equals 1. Plug that into your derivative, and you would be getting 2. So these are your solutions. I just want to point out something over here for this one. So I'm not going to solve this, but whenever on your test or it's mentioning determining the derivative from first principles right over here, it just means use limits. So why they're going to put first principles is for future chapters we're going to do is we change up the derivatives and find it from shortcuts. So whenever it says like find the derivative, you would use those specific rules. But sometimes teachers do find this derivative from first principle. So whenever you see first principle, you're not going to use those rules shortcuts. You have to use limits. So you guys are going to encounter this problem a lot. So it's going to ask you to determine an equation of the tangent to the graph of fx equals 1 over x at the point where x equals 2. So the key thing here is the equation of the tangent. That's what we're trying to find. And the equation for that, what we're going to use is we're going to use this formula, which is y minus y1, which is a point where x1 is already given over here for us. So x equals 2. And I know I can find the slope m by finding the derivative of the function given. So I wrote my formula over here I'm going to solve it by using limits. And all I need to do is plug in x plus h into my x, which I'm going to get 1 over x plus h minus 1 over x and all over h. So I did green over here. I'm going to just solve this separately first, just to not confuse you guys. And I moved it to right over here. So I have 1 over x plus h and minus 1 over x. What I need to do is make the denominator same so I can actually subtract them. So I'm going to multiply this side by x. I'm going to multiply this side by x plus h. So now I put the denominators together. I realize if I expand this further, I'm going to get x minus h. So remember to distribute this minus over to the x and an h. And I'm just going to say over x plus h again, so I'm not going to expand that. But what I realize is this is positive and this is negative, so I can actually cancel those out. And now I'm actually left with my negative h all over x plus h. So now I'm going to plug this back into the original place, so which is right over here. I realized to divide these, I can just turn this side into 1 over h and multiply them together. And I realize I can actually cancel these ones out and have limit as h approaches to 0, -1 because we canceled the h's out, all over x plus h left over here. And now I can actually go ahead and plug in my 0 to my function, and I'm going to be left with -1 all over x squared. So now that I found my slope, which I can just say, okay, I like to put these on top of my function to see which one I got it done. These we don't need to find anything because you're going to find the function, so you can eliminate those two. So what I need to find is x1 and y1. x1 I already have because it's 2, so the only thing I have left is trying to find y1. So how do I do that? You can actually do that by just plugging in 2 to my original equation itself, and you will get the y value. So when I do that, I found that my y value is 1/2. The only thing before plugging in my m value is, because it says x equals 2, it wants us to find the slope for that point 2. I need to plug in 2 into my x. So when I do that, I would actually get the m value at x equals 2. So that would be -1/2 squared, which is -1/4. So you're just going to plug that in, and here you go. This is your equation. This question asks for determine an equation of the line that is perpendicular to the tangent to the graph, and the same function given exactly the same point with the previous question, and that intersects it at the point of tangency. So what's different here is now it's saying find the equation of the line that is perpendicular to the tangent. So not the slope of the tangent, but what's perpendicular to it. So if you look at this graph, if this is my tangent over here, what's perpendicular would look something like this. And when we're trying to find with an equation, when we're trying to find what's perpendicular to this tangent, what we do is take the slope that we found, which is right over here, and take the negative reciprocal of it. So when taking negative reciprocals, what we do is take the slope, times it by negative. So just take the negative side, and when you do that, you would get +1/4. So that's the negative portion. I think of it that way. And take the reciprocal of it. So that would equal to 4. So now the slope that is perpendicular would be 4. Now my equation turned into this. So I already found the equation of the line that is perpendicular. So not always it's going to say perpendicular. Sometimes you guys are going to encounter find the normal to the graph. So normal means exactly the same thing as the perpendicular. As you guys see on the graph, it says normal. Maybe you guys realize it beforehand, that it doesn't just say perpendicular normal. So whenever you see the normal, you do the exact same thing. Take the negative reciprocal and you will find the solution. So there are some cases where the derivatives does not exist. So we're trying to differentiate the existence of the derivatives. So a function is f is said to be differentiable at a if the derivative of a exists. So whenever you see differentiable, it just means the derivative exists. At points where f is not differentiable, we say the derivative does not exist. So there are these 3 common ways that you guys need to learn, that whenever you see this, at that point the derivative does not exist. So let's say for cusp, whenever you see a cusp at the point A, it's not going to exist. Same thing with a vertical tangent, it's infinite in terms of derivative, it's not going to exist. Same thing if you tie back to the continuity section for 1.6, at a point, because there's a jump, it's not going to exist. So a question you guys might see in terms of this derivative being existent or not, this question says show that the absolute value function fx equals the absolute value of x is not differentiable at x equals 0. The first thing I realize, I can't really draw a unique tangent from the point 0, 0, because first of all, it's a single point, and also what we call a corner at the point 0, 0. But that's not only the way we can just prove and explain, oh, that's just because it's a single point. I can also prove it algebraically. If we use the one-sided limits that we learned and say, okay, I'm approaching to 0, and if I approach from the left side, my slope is -1. You don't need to solve because it's a straight going down. It's going 1 by 1, so it's -1 anyways. Same thing from the right side. Right side is right over here. Right side, the slope would be, if it's approaching like that, it would be 1. So I already see that these don't equal to each other. And we said if your left side and the right side does not equal to each other, then it does not exist. If limit does not exist, it just means the derivative does not exist. If the derivative does not exist, it means it's not differentiable. So other ways we can show derivatives is, we are familiar with this notation. We are always use this notation up to this point. But because fx means the same thing as y, you can also see a notation like this. And another notation is Leibniz notation, where it is dy over dx. It means the exact same thing as any of these notations. It just means it's a notation for derivatives, but it can also be shown in this form. So when you're reading it, you say the derivative of x squared. In this case, that's the function. So what it does is it removes the y from here and puts it here. Same thing. But we say the derivative of x squared with respect to x, and then it equals something. So these are just different ways that they can show you. Just don't get confused over it. They just mean exactly the same thing. In this one, it wants us to state the domain and on which f is differentiable. So I'm gonna go fast. But for A, I already see, we already mentioned that it exists at any point except this point, which I can say x does not equal to -2, and we just put these together. For B, I can see that it does not exist at the point 2, so I see the exact same thing, but now it just does not equal to 2 instead of -2. For C, that it actually exists for everything, and it doesn't really have anything from the cases we saw. So it just exists at every single point. It doesn't have a jump, it doesn't have a break, it doesn't have a cusp. For D, I already see it's a cusp, so automatically I look at the point where the cusp is at. It's at 1, so I'm just going to say x exists at all real points except the x1. For E, it exists at every single point because it doesn't have anything that will give us the information that it doesn't exist. It exists in every single domain. And for this one, I see that here from x2 and onwards to the right side, it exists. So how I can write this is, it exists at all real numbers except that it exists after 2, so x is bigger than 2. So that's it for these ones. So a word problem. So an object moves in a straight line with its position at time t seconds given by this equation, where s is measured in meters. So I already know my x is t and my y is s. Find the velocity when t equals 0, t equals 4, and t equals 6. So if you actually put it in a graph, this is approximately like what you will get. And I see that in order to change it from position to velocity, I need to find the slope at those certain points. To change it from position to velocity, that's what we do. And in order for me to find that instantaneous point, which we also called instantaneous velocity, that's what we found with limits. I can actually take the derivative of the equation and find that. So all I did is write the formula out, and I plugged in t plus h back into the original equation right over here. So that's what I did in here. So when I do that, I get this. Now I expanded it further. All I need to do is see if I can cancel out stuff. I see that I have a positive 8 and a negative 8t over here, so I'm just going to cancel those out. I see that I have a positive t squared, and if I distribute this negative, I'm going to get negative t squared over here, so these are gone. Just to distribute it, I'm going to change this sign into negative and this sign into negative as well. So I'm going to rewrite this again. So now I got an equation where I know from the numerator I can take h out and cancel h's. And now I'm going to cancel out the h, and now I'm left with negative 2t, negative h, and plus 8. I can go ahead and plug in 0 for the h, and I'm going to end up with negative 2t plus 8, and that's going to be my slope. Now, all I need to do is plug in the values that they want me to. So for t equals 0, if I plug in 0 for my slope right over here, I'm going to end up with for s and the derivative, where it says 0, I'm going to end up with 8. For t equals 4, if I plug in 4 for my t over here, I'm going to end up with negative 2, 4 plus 8, which is going to be 0. And that kind of proves it, because here 4 is right on the top, where if I draw a tangent, it's going to look like this, and the slope of that tangent is 0. So I already know I'm on the right track. And t equals 6, and I can write that as -2 and a 6 and a +8. So that's going to be -12 plus 8, and that's going to equal to -4. So those are my solutions. So for this question, it's going to be mainly based on limits property. So if you want to review that, it's the video 1.6 on our channel or on the website. So for this one, it says for each function, use the definition of the derivative to determine dy over dx, where a, b, c, and m are constants. The only different thing is if you're not familiar with the use of dy over dx, that's the only confusing part. Other than that, it's fairly easy. So for a, what I'm going to do is for d over dx, and remember, we're just going to put the y over here as a bracket. So I'm just going to raise the y and just put the whatever is given, the equation y, because y equals c, in here. So I see that if I take a limit of any constants, this was the first property that we went over, it's just going to equal 0. So for part B, I'm going to do the same thing. So I'm going to say dy over dx and put whatever the equation is given. So y equals x, therefore I'm going to put x in the place of y. And this is going to equal to 1. Because remember, again, in limit properties, anything of a limit where, let's say, xa approaches a and the equation given is a, it's going to equal to 1. So another thing I think of whenever I do d over dx, I think of that x over here erases whatever x is here, so it just takes out 1. So over here you can think of, because there are no x's to fill out or take out, it's just 0. It's just a way of thinking, it's not really mathematical. But over here I have 1x that it can cancel out 1x, just divide them, and if you divide x by x, you're gonna get 1. So for part C, I have d over dx and mx plus b. Again, limit properties where I can actually distribute the limits to each one of these. So that's what I'm going to do. I'm going to do d over dx mx plus d over dx and a b. The easiest part is I already know this is just going to be 0 because b is a constant and I don't have the term x. For this one, again, think of x as being cancelled. Well, if I do that, if I replace x, all I'm going to end up with is m. Part D is the most complicated one. It's going to be d over dx, ax squared plus bx, and a plus c. And you would distribute this into the equation again. So I'm going to end up with ax squared plus d over dx, bx plus d over dx, and a c. All I know is I found 0 over here, so I know this one is just going to be 0. For this one, it's really similar to what we did in part C, where it's just like these cancel out, so I'm going to end up with b from here. I already know that. For this one, you can actually think of, like I said, x is taking 1x out. So that's what I like to think. Normally we will learn about the shortcuts of derivatives. Because I don't have space, normally you can use it by limits and find the limit of ax squared. So I'm not going to do that because I don't have space. So I'm just going to write what it came out as. So it's going to come out as 2ax plus b, and that's going to be your answer.